Okay, thank you. I would like to thank again the organizers for giving me this opportunity. I have enjoyed a lot to prepare and give these lectures. In this last meeting, we will deal with the polar decomposition. And the polar decomposition is given by two factors, the partial isometric factor and the operator modulus. So we will study those factors as maps in certain infinite dimensional homogeneous spaces associated to operator ideals. So as an introduction, we recall that we work in a separable complex infinite dimensional Hilbert space, P of H, the algebra of bounded operators on H. So we treat with the following special class of operator ideals. Symmetrically normed operators ideals are two-sided ideals such that the following three conditions hold. First, this inequality, then this inequality is between the operator norm, and here is the uniform or usual operator norm. Then the second condition is a normalization condition. And the last condition is that with the operator, with the ideal operator norm, the ideal is a Banach space, we will treat with proper operator ideals. Some examples are the compact operators, the P-Schatten ideals for P greater or equal than 1. And these other ideals associated with symmetric Narman functions that we studied in the first lecture. We recall that these inclusions must hold where F is the set of final rank operators. We will use the following two Banach-Lie groups associated to an operator ideal. We have the restricted invertible group given as follows. It is a Banach-Lie group with the topology defined by this metric. And the restricted unitary group, which is given as follows. Both groups are connected. That's a consequence of the analytic functional calculus, because we can show that the exponential map is indeed onto. So some notation here, CR will be the set of closed range operators of our Hilbert space. And sorry, CR plus will be the positive closed range operators. Here, positive is in a non-strict sense, and PI will be the partial isometries. So from our previous lecture, we know that for every closed range operator, the Moore-Penrose inverse, T dagger, is another closed range operator defined by the following four conditions here. And the polar decomposition, we will use this notation. VT will be the unique partial isometry satisfying this condition with respect to the null spaces. And here is the modulus of T, defined as follows. So for closed range operators, we have this equality here. We can describe the partial isometric factor as follows. So in our previous lecture, we studied the Moore-Penrose inverse. This was motivated by the finite dimensional situation because the Moore-Penrose inverse is, of course, relevant to understand linear systems So in finite dimensions, there are a lot of works dealing with perturbations of the Moore-Penrose inverse. So we try to mimic that situation in our infinite dimensional context now. So we fix an operator A and a symmetrically norm ideal S, and we consider these sets of perturbation of A by the ideal. So here we have a well-defined metric given by the norm of the ideal. So we study the Moore-Penrose inverse mu in this set of perturbations. Now, in the lecture of today, we will study the two functions given by the polar decomposition, the operator modulus, and the polar factor in the same set of perturbations. Of course, to study the operator modulus, we will need to study the square root, but we will generalize our study to other functions, the class of monotone operator monotone functions. We will define it soon. So for the square root, we need to consider these sets of perturbations. We start to, our initial motivation is to study the operator modulus. So we pass from this set of perturbations to this set of, we want to study the perturbations of the square root to understand the operator modulus. So our set of perturbations will be now positive perturbations to study the square root. But note that here we first need to understand if this map is well defined, because we begin with an operator D here, such that the difference with C is in the ideal, and it is close range and positive. Then when we took the square root, we must have that the difference with the square root with C is again in the operator ideal. So we will see here a simple example to try to understand that this may fail because, for instance, if our operator ideal is the trace class operator ideal, take C equal to 0 and D a trace class operator such that its square root is not in the trace class, then we will have that this difference between the square roots obviously is not in the trace class. But this example is not exactly our situation, because if we want to construct such an operator, we will need to have infinite singular values. And since operators in the trace class are compact, those singular values have to accumulate to 0. So that will mean that the range of D is not closed. But we see that this is a situation that we must look with some care. I will present two results about this. The first one is the result by Powers and Storman. If we have two operators, positive operators, then we have this inequality the square root between their differences must belong to the Hilbert-Smith ideal if we have that this difference here belongs to the trace class ideal. This was not the main objective of their work. They were studying this condition when these differences of square roots belong to the Hilbert-Smith ideal, because they wanted to study unitary equivalence between certain states in the algebra of canonical anticommutation relations. So this condition is related, the condition that the square roots belong to the Hilbert-Smith ideal is related to the equivalence of that class of states. But here we have that our ideal changes. We have another result by Ando and Van Hemmen, where we can use the same ideal to compare the square roots. But now we have this hypothesis here that the sum of these square roots must be positive for some constant mu strictly greater than 0. We can see a proof because this result, because maybe we would like to understand this condition with the square roots of this sum here. So the proof is short. We denote the trace norm as follows. So we assume that this difference is in the trace class. If it is not, there is nothing to prove. So we consider here pi the projection onto the Calkin algebra. Since this difference is compact, then we have this equality in the Calkin algebra, and using that the Calkin algebra is a C-star algebra, we have the uniqueness of square roots. So we get here this equality, so that this difference is again compact. Now we put t to the sum of these square roots and s to the difference. So we note this identity here between the anticommutator, here is a half, and c minus d. Since S is now compact, we take an orthonormal basis of eigenvectors. We denote them as follows. So we compute here the trace of the modulus of C minus D. We use the identity here. And then we use a well-known inequality using the convexity of the modulus here between the inner products. Then in this step, we use that these are indeed eigenvectors. The half here cancels. And now in this last part, we use our hypothesis about the sum of the squares, which is bounded from above by some mu. So we arrive at the one norm of the difference between the square roots. In the same article, Ando and Van Hemmen generalize this result in two directions. First, the symmetrically normed ideal can be, the trace class ideal can be changed by any symmetrically normed ideal. Then they also took a more general class of functions. We know by elementary spectral theory that the square root satisfies this condition here. So this is the condition that can be generalized to define operator monotone functions in the positive real x. Some example here, the Earth powers, where R is between 0 and 1. These are operator monotone functions. This is known as the Lerner-Hens inequality. For R greater than 1, it is false that these functions that are not operator monotone. And we have another examples here with the logarithm and this fractional function. So the generalized result of Ando and Van Hemmen is the following. This is a slightly different condition. They assume that now the sum of the operators is bounded from below instead of the sum of their square roots. So if this condition holds for every F operator monotone function and S a symmetrical normal ideal, we have that whenever C minus D is in the ideal, then F of D minus F of C is again in the ideal, and we have this estimate here. The main tool to get this generalization is a result about operator monotone functions. Indeed, this class of functions is a subset of what is known as the peak functions, because operator monotone functions have analytic continuation to the whole plane, except for the negative real axis. And this class of peak functions are holomorphic functions that map the upper half plane into itself. So they admit this kind of integral representation theorem. Here V is a positive Borel measure satisfying this condition. So using this representation, they were able to prove this more general result. For instance, here is the formula for the square root, and the measure mu is given as follows here. So using this result, we have that the functional calculus of operator monotone functions is continuous if, for instance, we restrict to strictly positive operators, strictly positive invertibly operators, sorry. For that class of operators, we, of course, can get a bound like this locally. So this condition, this estimate here, will give us the continuity in the set of positive invertible operators. But using the ideas of Ando and Van Hemmen, in particular this integral representation, we can prove more. We can prove the following. This is a joint result with Pedro Massey. We have F, an operator monotone function with the integral representation as above, and we fix C, a positive invertible operator. Then the map from this open set to this affine subspace, given as follows, is real analytic. For instance, a local representation at the point C is given as follows, where here the functions f1 are given using the integral representation as follows, and the formula changes for all the other fn. So these are the homogeneous polynomials that we use here to prove that the function is real analytic. An important remark here is that we have we want to study the analyticity of operator monotone functions in this set where we have the operator C fixed. So in this set, we cannot use some results from analytic functional calculus because this is not contained in any Banach algebra. For instance, if C is the identity, in that case, we can use results from the analytic functional calculus because this open set is indeed contained in what is called the unitarization of the symmetric norm ideal. So we can use results from analytic functional calculus, but in our case not. So we must go to this integral representation to prove this result. Now we will use that result to study the operator modulus and the polar factor. So returning to our problem about the operator modulus, we have this map alpha, which is the operator modulus. To understand that map, of course, we need to understand the square root. That is, we take our fixed point, now C, as A star A. So we study the square root from this set of positive perturbations. So this leads us to find a decomposition of the set of positive perturbations by an operator ideal, which is these sets. And such kind of decomposition should be useful to study properties of our map alpha. We would like to study, in particular, differentiability properties if this map restricted to some sets contained here in the set of perturbations. We would like to know if restricted to some sets, this alpha is real analytic. So an important remark here is to note that our set of perturbation is invariant by this action. This is known as the congruence action. We are acting here with the invertible restricted group. So I would like to recall what is known in the case of the bounded linear operators of a Hilbert space. Here, we do not have any operator ideal. So we take again the class of closed range operators here in a Hilbert space, and we decompose the class of all positive closed range operators according to these two dimensions here. Then for every operator C fixed in one of those sets, we have that there is that the congruous action indeed he gives here a transitive action So these sets are indeed orbits, and they prove more. These are indeed smooth homogeneous spaces of the usual invertible group. This means that they can prove that the isotropy group is again a Lie group in the uniform topology, and its Lie algebra is closed and complemented in the Lie algebra of the invertible group. And then they studied the submanifold structure of these orbits. So they studied the induced map by the action, by the congruence action. It turns out that this map has continuous local cross-section if and only if n or m are finite. The idea behind this is to construct the continuous local cross-section. They need the continuity of the Moore-Penrose inverse, and so that they need to move in certain set where you can get that continuity. So in our setting, the notion of dimension will not be useful. We will change that notion for this notion of the index of pair of projections. We recall here the notion, we had already studied this notion in the previous lectures. Recall that a pair of projections, PQ, orthogonal projections, is said to be a Fredholm pair when this operator, viewed as an operator from the range of P to the range of Q, is a Fredholm operator. In that case, the index of the pair is defined as the index of that operator. And we have that the index can be also computed as this difference between dimensions of these intersections. Some properties. The first one is well known. If we have two orthogonal projections such that this difference is compact, then the pair is a Fredholm pair. The second here will be relevant to our study because whenever we have two close range operators such that this difference belongs to the ideal, and then of course this difference is compact, then we know that the associated projections onto the corresponding null spaces are is a Fredholm pair. Indeed, we proved this result the last lecture. And also, a useful property for us will be the following. If we have two Fredholm pairs, where here one projection is repeated, then the index can be computed as the sum of these indexes. But here, one needs to assume that this difference or this other difference is compact. If not, the result is false. This is, for instance, proof in the work of Avron, Siller, and Simon about the index of two projections. We already mentioned that work. So what we did in the second lecture to study the Moore-Penrose inverse is, in our set of perturbations here, the operator A is fixed. We decompose that set using the second property of the index from the previous slide. We know that this index between the difference of two close-range operators, this index is well defined, so we will decompose in disjoint sets according to the value of that index. We will call these sets Ck of A. Note that here K is in this set JA, which can be completely described using these dimensions associated to our fixed operator A. It can be shown that there are always infinitely many Ck of A, but what is important here is that this action here, that for a close-range operator moves the null space and also the range, turns out to be transitive in each of these sets Ck of A. And we prove that these Ck of A are also homogeneous spaces, smooth homogeneous spaces, and submanifolds of this ambient space. Note that what we are saying here is that these sets Ck of A are orbits. For instance, when this K is 0, we have that this is the orbit of by this action of the operator A, that it is fixed. But for other different values of K, non-zero values, we have that these sets are orbits, but with respect to some close-range operator that has index K with respect to the operator A. Well, then using this set Ck of A, in our previous lecture, we showed that this map, when restricted to that orbits, turns to be analytic, real analytic, and also its inverse is real analytic. So we will try to imitate these ideas now in our context with the operator modulus and the polar factor. Now we have this decomposition for a fixed positive close-range operator C. It turns out that this set of perturbations can be decomposed again using the index with respect to the projections onto the null spaces. And now these are again orbits by this congruous action, and we can show again that these are real analytic homogeneous spaces and submanifolds of the natural ambient space. I will not go into the details of this because this is more or less similar to our previous lecture with that different orbit. And we can also, to understand the polar factor, fix a partial isometry V, and by a similar idea, give a decomposition of this set of perturbations of the partial isometry V. But now the action is as follows, moving the initial and the final space of the partial isometries by these restricted unitaries. Indeed, I worked in this problem long time ago. These results are from a paper about 15 years ago. So I was trying to understand a sort of Stifle type infinite dimensional manifold associated to operator ideals that should be a kind of analog of the restricted Grassmannian. So I studied this type of partial isometries and this type of perturbations. So our main result here is that if we fix an operator ideal, a symmetrically normed operator ideal, and we fix also a closed range operator with this polar decomposition, then the map given by the operator modulus and the map V given by the polar factor are real analytic fiber bundles. Note that what we have here is a result between functions defined between orbits that are Banach manifolds. Recall that each of these sets, Ck of A, Pk of the modulus, and Vk of the polar factor, as we said in the previous slide, are indeed orbits of the corresponding action. In particular, we know that for the case of k equals to 0, we have that C0 of A is the orbit of the operator A, the following orbit, and similar to P0 of the modulus and V0 of V of A. So I would like to give some ideas in the proof. First of all, one can show that these maps are indeed well defined and they are untrue. This follows more or less immediate by using properties of the ranging, null spaces, and the index of the operators. We will explain later with more detail why alpha is real analytic. But once we know that alpha is real analytic, the polar factor can be expressed by using alpha and the Moore-Penrose inverse. So we get that the polar factor is real analytic. I would like to show you how the fibers, the form of the fibers here. Suppose that we fix C0, a positive operator in this orbit, then the corresponding fiber is given by moving the partial isometries, but that partial isometries must have the same null space as our fixed point C0, and one can see that this is indeed isomorphic to these sets of partial isometries with respect to a fixed partial isometry. Indeed, any partial isometry V prime satisfies in these two conditions, that this difference belongs to the ideal and this condition about the null spaces. The condition here with respect to the null space of C0. In our previous lectures, we have studied this set of partial isometries with a fixed partial isometry V prime. We had that this set is indeed again an orbit, but an orbit given by moving only the range of the fixed partial isometry V prime we move that range by using unitaries in the restricted group. And we already know that this set is a Banach manifold, indeed a homogeneous space and a submanifold. Then we try here to understand the fiber of a fixed point V0 of the map V given by the polar factor. Now what is moving here is the positive operators, now denoted by this C, but they must satisfy this condition. But what we know about the uniqueness of the polar decomposition. And it turns out that this is isomorphic to an orbit, but in a smaller subspace, we have to consider here the pk of C prime, by where C prime is a fixed closed range operator in a smaller subspace given by our fixed point V0. I will not give the details, but once one knows the fibers, then one can go further and construct the analytic local trivializations to get the analytic fiber bundle structure. This can be done by using the fact that our homogeneous spaces, here the pk and the vk, admits real analytic local cross sections. Using that and the form of the fibers, one can construct then the local trivializations. So to finish, I will like to give some details of the proof of this fact here. The fact that alpha is real analytic.
It rose up. Can you hear us? Do anything.
I can write in the chat.
Or he's German. I cannot.
So not the Hilbert. Elliptic scenario.
For your family, check if they're okay.
We're fine.
Need the WhatsApp connection is also by internet.
Sí, te esperamos.
Okay. But they said that his possible connection by WhatsApp would also be by.
Probably was temporary, just for a minute. Oh my God.
We can see through.
Right. Yeah, because in the limit is outside. It's. I will just try to approximate this out to it's not.
He wants to enter,
Hello, sorry for the interruption. I will share again.
Loud because it's okay.
Mm. Should I finish the proof or not?
I computed that you have 5 minutes.
Okay, so we want to see why alpha is a real analytic map. And from what we know from the previous slides, we have that the square root of any other operator monotone function is real analytic in the set of perturbations associated to invertible positive operators. This is because we need to use Ando and Van Hemen's condition about the sum of the two operators is bounded from below. So now we want to pass to the more general setting of closed range operators in our orbits. The idea is to use this result if we have a fixed subspace S, then one can associate to each T in this restricted invertible group a unitary in the corresponding restricted group, such that this condition about S holes. So we use this condition with S being the range of our fixed operator C here. So what we have is that the map here that sends G to this quantity here, that note that this is the same as saying GC G star, because the unitaries here by the functional calculus cancels with the unitaries outside the square root. So we write this map from the restricted invertible group to our congruence orbits as the following three factors here. This uj, here uj star, both are real analytic in terms of G, because our lemma here above, and now here in the 1-1 entry of this decomposition with respect to the range and the null space of C, we have a positive invertible operator. So we can apply our previous results in this set. So we get a factorization here in these three factors. Each one is real analytic. Then we can use that we are working in homogeneous spaces and we have a real analytic cross section to go to our congruence orbits and get this result. And then from that, it easily follows that this map is indeed real analytic. So I finish here giving some references, the paper of Ando and Van Hamen. This is the work about the index of pair of projections by Abram, Siller, and Simon. This lecture was based in these two works with Pedro Macei, and here the work by Korach, Mastripieri, Stojanov. The relation about the peak class and operator monotone function is described in this book. Well, some books about operator ideals, Gover and Cranes and Simon, and this is the work of Power and Stormer. Thank you very much.